All right, so dynamic polymorphism. What's more exciting a day before an assignment's due than talking about something that's unrelated to an assignment? Very little. Very little. But it's still a fun little topic. There's a few keywords we've got to get out of the way before we start. First one is inheritance with no N. There is an N that's meant to be in that particular word. Inheritance is the ability to create new classes based on existing ones, right? Again, you should know this because you've done an object-oriented course before this course. So I have one class. I say I want to create another class where it's a template, and then I add functionality to it. The examples that you get taught in courses like Comp 2511 for undergrads are that you have like, a class that's like animal, and an animal might have like a name, and it might have some category, and then you create another class called dog, where dog inherits animal and all of its properties, but it has some extra stuff like maybe its breed and whether it has a collar or something that doesn't apply to spiders, because spiders don't have collars as far as I know. I don't keep spiders, but I doubt they have collars. So that's inheritance. Polymorphism is also a word you should be more familiar with, but I think it more easily goes under the radar in terms of understanding. And basically, polymorphism is a way where multiple things can be treated as if they are the same, right? So what that means is, again, if you have a function that takes in an animal and prints out a detail about an animal, polymorphism in programming languages allows you to pass in an animal type to that function, but also anything that is a subtype of animal. So you can pass in a dog or a cat or an insect class. If all of those classes inherit from animal, then they can act in place of animal. Basically, a type can imitate its parent type that it inherits from. That's kind of polymorphism in the context of this object-oriented world. And that word is important because this lecture is called Dynamic Polymorphism. We have two lectures on this topic. One is called Static Polymorphism, and the other is called Dynamic Polymorphism. Dynamic polymorphism is all about inheritance and a bunch of other kind of complicated stuff, whereas static polymorphism, which we talk about next week, is more about templates. You know, when you can create a vector of ints and a vector of doubles and stuff. All of that stuff is figured out at compile time. Whereas dynamic polymorphism has a big kind of runtime aspect to it. You could also call it compile time polymorphism or runtime polymorphism if you wanted to. And then we have a big word, dynamic binding, which is the runtime resolution of appropriate function to invoke based on the type of this object. Big word, don't need to worry about it too much right now, but basically what it's saying is that if I have a dog class and a cat class and an insect class, and I pass that into a function that takes in an animal, we have to figure out which function in code to actually call, which is a bit abstract right now, but it makes sense why that's such a problem as we unpack these topics. So if we look at C++ in general, what are the object-oriented tenets of C++? Well, we want to support object-oriented programming without a performance penalty. We want to support generic programming, which you've used with vectors and things like that. And so on and so forth. But if we think about that whole thing of lightweight abstractions in C++, which is a theme that we keep coming back to, we want a way to do subtyping, to do inheritance in C++ without it causing significant overhead, just like everything else we're doing. So it's all about doing what we do in other languages with less overhead. So bit of code here in So we have a bit of code here, inheritance in C++. What you have, and this kind of is a bit of revision, I guess, but applying it with what we've learned from C++. We have a base class here on our left, your left. We have a base class on our left. It has a public getter, two getters, and two private members, right? So no constructor or anything. So I mean, if you actually ran this class, it would default construct an int and a string and have a getter for each of those, and it would return a copy of those in both instances. So pretty straightforward. Base class doesn't really do anything. But then we could go and create a subclass like this one here, which also has an extra two members, which is a vector of ints and a unique pointer to an int. So now we have, how many private members does subclass here have? Well, it's complicated, I guess. Yeah, how many private does it have? we lazy or we scared? Yeah. 4? It's a good question. I think it's 4, but I get worried about some of the semantics around, oh, that's protected. Yeah, it has 4, right? So it has these 2 from the left plus these 2 from the right, okay? So it's like the base class has 2 properties. This class has 4 because it inherits everything from the left as well. How many functions does it have? How many member functions? How many methods, whatever you will? It has 3 because it's got the 2 public ones that are the getters, and then it's got a, well, sort of. This is where things get really weird, right? I misread that because the text is quite small for me to turn up my brightness. This one has 2 member functions on the left, sure, but the one on the right, it has decided to overwrite one of the member functions because it's using the same name, get class name. And instead of saying base class as an output, it's saying subclass as an output. Okay, well, how many member functions does it have now? Does it have 3 or does it have 2? This is kind of where the weirdness of all this topic starts to come. Now, obviously, if we had a different method here called, like Hayden as a peanut, we would have 3 methods because we'd have 2 from the left and we'd have 1 from the right, okay? But it's more complicated because they've been overriding. And those questions around, so how many methods does it have? What does it actually look like in memory when the object's created are very interesting. So things we skipped over. To inherit in C++, we do use the colon syntax. You've seen there. Class, subclass, colon, public, base class. Fairly standard stuff. Same general gist as other languages, though slightly different syntax. We know about visibilities, can be public, protected, or private. I do believe we covered that naturally back in week 3. As a general rule, you try and make everything private always, and something is public by exception. Also, when it comes to protected, that's something that whilst you can use, different people will have different views on whether you should use that, but most classes have private and public things. Yeah. Private base class and the maximum ability is private. Yeah, it's not really too important. So here's where things get interesting. We got our base class on the left, and we got our subclass on the right. Now, what you're seeing in this particular instance that is important is this is kind of like a way to view memory, right? Now, obviously, it's not that straightforward because vector member here is going to be bigger than a pointer member and a string and an int and something like that. But it's more saying that, as we said before, a base class needs to allocate memory for these 2 things when you create an object of it. Because remember, the class itself, I know I might be stating the obvious, the class itself does not kind of consume memory in general, right? Because it's just a type definition. It's like asking how much does the int type take up in the program. It's like, well, it's a type, it's a template. So when we create objects of that base class type, they all take up memory. That requires these 2 slots for the private members, and this takes up 4. Exactly what we said before. However, the class is aware that 2 of its members are from that sub-object, and 2 are from here. So it doesn't just kind of have this 4 properties and doesn't really know much about them. It's very well aware that it contains a parent class within it. Now, bit of fun code exploration here. Let's have a play. So what do we got? Code, what's it called? Codeexplore.cpp. There. All right, so we got our base class. It's what we had before. We have our subclass. It's exactly what we were looking at. Now's the fun part. We create a base class type. We create a subclass type. Right, now again, obviously, if we were writing this properly, we might say auto base class equals base class like this. But I like with new topics, we keep it really simple. That type, this variable, that type, this variable. And then we are going to call print class name for both of them. Print class name in this case is not a function of any of the classes. It's just a random function in C++ that decides to standard C out the class name and the get member as well. Right now, because get member in this case should also be 0 because we don't actually specify it anywhere. Who thinks they know what this program is going to print out? Someone tell me. How many people? 10 people on YouTube. You don't even have an excuse not to post anything. it's going to print out, you know, two strings. Let me break it down for you so you don't have to express yourself. It's either going to print out, right, BaseClass, or it's going to print out BaseClass subclass, right? Because the first one here is a base class and the second one's a subclass. And then we pass them in. Oops, sorry, my bad. That's very poor interpretation of code. Should do 0. It's annoying that we print out the 0 because I don't think we'd do anything with it. It's either going to print out one of these two things, right? Yeah. Who thinks something like that? It's probably not going to print that exact thing. I probably screwed something up. But who thinks it's going to print something along the lines of this first one here? Who thinks it's going to print something along the lines of the second one here? Okay. Ooh, mystery. All right, well, let's go do it together then. So I'm going to make code explore. It's already made, hopefully. Yeah, that wasn't inspiring. Oh, build. Goodness. No. Oh, God, sorry. I know, like, there's a few of you here who've been like working on C++ for like 3 hours a day, and you're like, rookie. Let's run it. BaseClass. Terrifying stuff. What a terrifying language. That's confusing, because we called print class name with a subclass, we passed it in, and then it decided to just print out BaseClass, even though it's a subclass. We overwrote it, right? You following why it's confusing? Because you should have like overridden that function. Let me, just for fun, tease something else out. What if I made a different variation of this one? But instead of taking in a base class, it took in a subclass itself. Instead of being called base, it was called sub, whatever. And then what happens if I called this, actually I should give it something else, another name. What happens if I called it now a second time with a different function? But that function's only difference is that the type that it takes in as an argument is now the subtype itself and not the parent type. Let's see if this has any impact. Ah, there you go. So now we're printing out a subclass. Now this is really interesting because you got to think again about, you know, imagine you're building a compiler, right? To understand these complicated languages, if you think like a compiler, things might start to become easier because you think, well, in this case, someone gave me a type and they told me it was a base class. So what I'm going to do is I'm going to go look for base classes method called print class name, you know? Even though they gave me something that I could polymorphically interpret as a base class, right? Like a subclass is a base class with more, I'm still kind of digesting it as a base class. So therefore, that kind of gets printed out. Now, it's a bit more complicated than that, which is where we get into some keywords and stuff. I'm not going to go into... yeah. And it's also this is also the tricky thing. Big detail I just forgot here. The part that really gives us the kicker is largely to do with the fact that we are copying this in. Like exceptions and stuff, the rules get a little bit different with references, but in both of these cases, we are copying the object from our main function into those sub-functions. And if you just think about it from the compiler's perspective, the compiler has been told that a base class is the size of an int. Right? That's the only member it has. It's just an int. Well, plus probably some other, you know, BS going on in the stack, but it's just got an int. So when you take a subclass, which might be this big, and you pass it into a function that's expecting you to copy something smaller, that big, it just cuts off the bottom of it. You know, it literally just rips it off because it's like, I only have space for one int. So I appreciate that you've got like this subclass with like 2 ints in it, right? Like the int from the parent and the int from the child, but I don't have that. So I'm just going to get rid of it. This is actually what we were talking about with exceptions. I think hope I'm getting the terminology right, which is like the whole object slicing problem. This is actually why we talk about not throwing exceptions by copy, but always by reference too, because exceptions use inheritance quite extensively, right? You have like the standard exception and then the logic error and then the like out of range error or whatever. And each time you go down that kind of inheritance tree of exceptions, they get a little bit more information in them, you know? So if you pass like an out of range exception into something that catches a standard exception, just a really quick example, imagine you've got some code and it throws a standard out of range, something like this, but you're catching somewhere else in the code a standard exception, E. The problem is that when that out of range exception, which is a subtype, so maybe bigger, has to get caught by the catch, passed in as a copy, it just strips off everything that is associated with the subtype, right? So basically the copying of an object, if you're doing it polymorphically, will just erode it down to its parent type. And that's why we do things by reference, because when we do things by reference, it's able to point to something bigger, right? Again, if that's a little hard to follow, let's just keep going for now. So the question was like, how can the compiler allocate space for a base class when it doesn't know how big it could be? And that's kind of a variation of what I just said. This is what we call the object slicing problem. We had that problem with exceptions. The conclusion of this is to use references and/or pointers, but preferably references, when it comes to polymorphism in C++. If you're still a little bit confused here, what I'm saying is pretty sort of manageable. Let me just get rid of this stuff for a second. What I'm saying is you have a base class and you have a subclass. It's fine to do like these two things here. I don't know why you would be copying objects. I'm sure there might be a reason. But in this particular case, I'm copying a base class object into a function that expects a base class. So I'm copying the thing I'm passing in. Because of polymorphism in C++, it will allow you to have a subtype be given to something that expects a parent type. That's the same in Java. It's nothing really new. And then quickly I can also pass in a subclass to a function that takes in a subclass. But if I try and shove this subclass into a function that takes a base class, it will accept it. That is polymorphism. It is a polymorphic language. It's just that because it's a copy, it just has to rip the bottom off because there's only so much space. That's called object slicing, referenced on the slides. I'm just explaining this a few different ways here, really. And the way we would get around it, as you can see with this code example, is that we would define this class to take in a reference to that base class. Now, this makes sense because a reference is always a pointer. So if you have something that's, if you have a base class type that's referring to a base class or a subclass, it doesn't matter if the subclass is twice the size of the base class, because this base variable here is just a pointer. It's just going to be an 8-byte pointer under the hood referencing something. And therefore, let's have a look at how our results might vary. So if I just get rid of my so random. If I just get rid of my extra function here today, we try that again. Now, obviously, we're still doing the copy for now, so we're going to get the copy result. What happens if I change it to a reference? Oh, no. We're still having problems. Sorry if you didn't catch it. I was a little bit jittery there. I'm still getting base class, even though I passed it in as a reference. So nothing's being sliced anymore, Like what I mean by that is this base here is a reference to a base class type polymorphically, but it is actually referencing the entire object. So it's referencing the correct object with all the bytes in it. Nothing has been sliced, nothing has been cut off, but I'm still getting the wrong function. And that's because even with a reference, it's still trying to print out the base class's version of that function. This can be changed with some extra code features in C++, which we will come to in a second. But this is one of the headier topics. I'll admit that straight up. So getting to this is kind of what we're coming to. It's like this is just the same kind of code broken up here. How does the compiler, in this case, even with the references, so no object slicing, how does it decide which version of getClassName to call? Because you're giving it a subclass with this version, but the argument type that it's taking in is of type this version. So it's got to pick one of them, right? Now again, if the class took in a subclass, it would be fine, but it's taking in a base class. So how can we ensure that calling getMember, how can we ensure that it does the right thing and it doesn't have a big overhead? And this is where the key syntax virtual and override comes in. So there are two keywords in C++ called virtual and override. I don't know why, they remind me a lot of like async await from JavaScript, if anyone's familiar with that, even though they have nothing to do with it, just because like they often come in pairs, like there's often like a virtual with an override. But let's say I have a piece of code like this, a really simple piece of code, subclass, and I try and print that subclass into the base class, same thing we've had before. By default, C++'s behavior will print the base class one. And it makes perfect sense if you think about it from an efficiency standpoint, because all this function has to go with is the type. Right? You're this function. You don't really understand, like even if you get a pointer to a base class, a subclass, a subclass, all you know is that it's a type reference to base class. So you're just going to be like, well, I should just look at whatever's in base class then and use that. That's a smart, lightweight implementation. So if we want to change it, what we have to do is in our base class, we have to flag any function that might be overridden as virtual, as a keyword in front of it. And then when we want to override it, we also flag it with a keyword called override on the right. Okay, so this is basically you sending a signal to the compiler that, hey, I know your default behavior is to be really lightweight, and just like use the invoked type, can't remember the exact word, but I'm telling you, I want you to think deeper. I want you to actually allow this to be overridden. It's not, I could be wrong, it's not the virtual that causes it to naturally go to the subclass, it's the override. It's just you can't override something that's not virtual, right? So the virtual keyword says this may be overridden. Override says I am overriding it. How does that work? That's an interesting question that we'll keep kind of coming to. Okay, well, override isn't always required by the compiler. You should always use it. Override fails to compile if the function doesn't exist in the base class. So yeah, it's how I described it was a bit more conceptual. In reality, as you can see here, it's not like it'll still work without it. I mean, we can kind of play around with this ourselves, right? Because if I come here and I make this virtual, let's see what happens now. Because previously, what happened? What is it complaining about? Has virtual function, but non-virtual destructor. Oh, I hate this one. I have a memory of it now. Oh. Let's just throw it in and see if it's happy. Override a member function, but it's not marked as override. All right, so linting rules looks like W errors suggest override. Yeah, okay. So whilst if you just G++ this, maybe it would tolerate it, right? Like if I just went back a folder into 7+1 code explorer. Yeah, okay. So like it'll work. I mean, maybe I'll just play with that then. Is that going to A.out it here? Yeah, so you can see in that case, if I just skip all our CMake compiler flags and stuff, it will, with the virtual function, allow it to be overridden. If I just try that one more time. Right, so see how that virtual has an impact there? So by default, without the virtual, it will just print. It'll be like, well, I'm a base type base class. I'm going to print the base class method. But with the virtual, it will see that it has been overridden in this case, and it'll be like, all right, because I marked as virtual, I know someone else might come and replace me that's a subclass, so now the compiler will look for any potential overrides of that. You can also see that I don't have the override flag, keyword, whatever, can't remember the exact term for it, but the way we've set up CMake, it will still complain about it and it will still want it here. So that's a lot like best practice, but it's not strictly required by it. And the reason for that is because override fails to compile if the function doesn't exist in the base class. What that means is that, if this makes sense, let's imagine that you're like, oh, I'm going to go override the function Hayden as a peanut. When you put override there, the compiler will fail if it can't find a function that you're trying to override. You know, it's not quite like no except, because like no except is a little bit more documenty and a little less protecty, because no except doesn't check if you haven't thrown an exception, right? But it's along the same lines of like good programming practice. It just means like, because remember in the big bad world, you will have instances where like you are overriding a function in a library you didn't write, you know, someone else wrote it. So what happens is when you mark that as override, it's like, oh, cool, the override's not needed and the code still compiles fine, but let's imagine the person who wrote the class that you're overriding decides to delete their function for some reason. You're going to get an error now that says only virtual members can be marked override. So here it is essentially saying you just wrote override, but you're not there's no virtual function in the parent class. And also, I mean, it'll catch you as well, as you can see, if you don't have the virtual there. So, you know, because without the virtual there, it's not going to override, is it? So again, all kind of good practice. Sorry. Oh, fun code, virtual.cpp. I love some of this code. It's really crazy. I tell this story whenever I teach this course, which is like the original version of this course was really compiler heavy. Probably mentioned that before. But long time ago, when I studied a course similar to this, the precursor course to this, and some of these code samples are actually still taken from that, we had to do an exam, and it was an in-person exam where they gave you pen and paper at Randbrick Race Course, and they would ask you questions. And they were the most evil questions that I remember, in a funny way. They would give you a piece of code like this, right? They'd like print it out, be on the exam paper, like you're doing your HSC, and then they would say, what does this program print out? And then they would give you option A, option B, C, or D, and you would color in the box, which I always thought was hilarious because it's like a hard problem to solve, right? Because there's always subtle things going on. But my favorite part was Jingling, who's one of my favorite course creators. He always decided to add an option E to every multiple choice, which was does not compile. So you would be like doing this exam, and every question you were not only trying to figure out like what weirdo kind of direction this would go, you'd be like thinking, oh, virtual override, if there's no virtual there, is that going to be a problem? But then you'd also have to be like, it won't even compile. He's very smart, so that stuff was fun for him and painful for me, I guess. But yeah, we got our base class here. With the virtual destructor, we've got our subclass, nothing new. We've got our print stuff there. Now we have some extra stuff in the main. So we're saying our subclass is a static cast of this every time. So what we're doing, we are creating a subclass, unique pointer, right? So we are mallocing a subclass to the heap. We are giving it to a unique pointer, and then we are casting that from a unique pointer to a subclass to a unique pointer to a base class. Now, this, just for those who are struggling with this, I don't remember exactly why we wrote this like this, but this is not that dissimilar to, again, a case of saying I'm going to create a subclass S and then say, like, I have a base class, you know, reference called B, which references S, right? This is just like the point. This is like the smart pointer version of it, because obviously I could also write this as like subclass star S equals new subclass, and then I could say base class star B equals S. So these are all three versions of the same thing, right? And I think this is the easiest to understand. You are creating a subclass, that's what you're creating, but in each of these cases we're creating a new variable. Well, I mean, this is slightly different because of the variable names. Actually, let me break it up. Let's really do this thoroughly together here. Is if I went and said like subclass star S equals that, and then I said base class b equals that. Now they're all saying the same thing, pretty much to a T, unless I've screwed something small up. This one is a safe malloc. We learned about that on Monday. Sweet. So these two do the same thing, just this one's going to get you in trouble. I haven't even freed it here either, have I? You know? So unique pointer is really important. And this one's just the reference version of it. But the whole point with this is that we can come along and create a pointer or a reference type to a subtype. So if I unwind all of that for a second, sorry. Now we have this subclass variable, which is a pointer. It is a base class pointer to a subclass type. Right? Polymorphism's funny like that. Because again, your reference type can be a parent type. And then when I say, hey, I want to print out subclasses get class name, well, what do we expect should happen in this case? Well, my quick reading of the code should be that we get a good result, which is that we should print out this is to do with destruction. So I'm pretty sure in this case that this is going to try and call, like if you call get class name, it will try and call this one and print that out. Right? Let me just get rid of these standard couts for a second, and I can just verify that I haven't misunderstood something. Make virtual 7.1 virtual. We get subclass. Great. That's what we wanted, because we're following what we said. If we didn't make it virtual, if I got rid of this and I got rid of the override, it's going to print base class. Again, I'm really honing the point in, because subclass, whilst we call it subclass, is a base class. Like, you really could rename this to be like, base class unique pointer to a subclass object. That's what it is. But the real question, which is interesting, and this is where I think these lectures can be quite funny, is what's going to be happening with these destructors here? So this is where my comment about jingling writing these questions is like, what is this program going to print out? Well, you know it's going to print out subclass now. Well, sorry, once I undo my wrong doing. But what else is it going to print out? So if I bring this up over here to the side again, I know it's going to print out subclass. What else is it going to print out? If someone wants to have a stab. Destroying base class. Destructing base class. Like that? Is that it? You sure? It's tricky. Let's try it out. Oh, should probably put a new line in those ones. Make it a little better. So it printed out destroying subclass and destroying base class. Thank you for putting your hand up and volunteering. You're the bravest person here. Because what happens is that when you destroy a subclass, it has to destroy itself and then call, like it has to kind of, not recursively, but kind of iteratively move its way up through the chain, right? So if I'm a subclass inheriting a base class, I have to destroy all my stuff, and then I have to destroy that base class stuff, and if that inherited something else, I have to kind of destroy that. That's the opposite of how it's constructed, because when you construct a subclass, it actually calls the constructor of the base class first, and then once that's done, it calls the subclass. If you remember Java, that's what the super function is, right? From constructors in Java. So but this is why the example has a pointer, because I could do something slightly different here to make another point, which would be what happens if I said I'm going to make a base class called B, right? Or auto B equals base class. And then I make another thing called C, which is like, what if I tried to static cast, subclass, I should call it S. So what happens if I had a subclass and then I tried to cast my subclass to a base class? What's going to happen here in terms of destructors now? or does not compile. So if I run, what's it going to complain about? Subclass does not refer to a value. Why? Oh, duh. Sorry. Okay. Still problems. Definition of implicit copy constructor for base class is deprecated. Is the user provided destructor? Goodness gracious. Let's just do it. Base class const base class reference BC equals default. Oh, sorry, probably the other one too. This is a spontaneous code demonstration. No matching constructor. Oh no, because there's no default constructor. Heavens above. Can we just default everything? That would be good. All right. Destructing base class, destructing subclass, destructing base class. Who thought it was that? Well, it's tricky because in this case we're basically doing a copy, you know. That's the problem with these static castings. You don't really think about it, right? Because we're normally static casting an int to a double or something, right? It seems really trivial. But if you think about it, we're creating a whole subclass, and then what happens is we are creating a copy of it. Okay, so now we have to create a whole other base class, but naturally, you know, object slicing because it's copy. So then what happens is the program ends, and we have to destruct the B we just created, which is a base class. Then we have to go destruct the S. So this happened because we made a copy of the thing. That's why we were getting copy constructor errors along the way, because it was like, I don't know how to copy construct this thing. So very fiddly stuff. The main point of that example originally was just to make you think about how destructors are called and whatnot. But this is where things get most interesting. And we'll do this for like 10 minutes and then have a quick break, which is Vtables. Vtables are the magic secret sauce that make all this stuff work under the hood, right? Because it's like, how does all that virtual stuff work? You know, what happens if you have like many subtypes and various other things? So a Vtable, each class has a Vtable that's stored in the data segment. So remember, the data segment of code is, like if I write a program, we've kind of talked about this before a few times, but if I have oh yeah, that's great, it's exactly where I want. The data section of code is something like this up the top. It's the part of the binary that compiles that just stores some metadata. And what we're saying here is that when a Vtable comes with classes that have virtual components, a V stands for virtual. So if you define a class and then you define a subclass, the compiler will just create two classes in the standard, you know, object-oriented inheritance rules. But once you start defining things as virtual, it will go and create a Vtable. A Vtable is the instructions of how to deal with this, and it will store it in this particular segment up the top in the compiled code. So it's not like it, you know, it just makes your binary bigger in that case. And a Vtable is an array of function pointers that say which definition each virtual function points to for that class. I don't want to try and word my way through that explanation because it's a bit confusing, and I think some of the diagrams make more sense. So let's try and jump ahead. This is a diagram, as you can see. It's a bit big. So when we look at something like this, and good example, we have three classes we're dealing with here. The first class is a polygon. The second class is a triangle. Third class is a rectangle. Triangles and rectangles are types of polygon. So polygon, triangle, rectangle, they both inherit from the polygon. What you can see is that the polygon, the triangle, and the rectangle, all three of them have functions for sides and area. So the polygon, because it's like a base class, it just decides to implement them both as functions that return 0 over here on the right. But a triangle, well, it's going to have three sides. So when you call side the sides function on a triangle, it returns 3. And if you call area, it returns height times width divided by 2. Now, ignore the vtable part for a second. The class polygon has a height and a width, right? I know there's not code in front of us, but you could imagine it pretty easily. It's like class polygon. It's got, private section, which is like int height and int width, right? So that's what a polygon looks like. And what we're saying is when we go and create these other ones, like class triangle, that inherits a polygon, or class rectangle, that inherits a polygon. In both of those cases, we don't add extra members because we only need a height and a width. But what we do is we do override the functions, which was, what was it? It was like sides, whatever, like int sides. There's some implementation of it, and there's some implementation of area too. So we do go and override those two things. So we would have to mark those as virtual. We would mark these as override. Then we would do the exact same thing for rectangle. So that's what's going on here. And again, the rectangle is going to be height times width. What happens is that for each of these classes, we also have a vtable. And a vtable is basically an array of function pointers for each of those functions. A little bit confusing. What I mean by that is imagine that every class has a list of functions, right? All the functions you've defined. And all a vtable is an array of pointers to various functions. And each vtable in this case, you could imagine each vtable here would be 2 function pointers, so 2 8-byte pointers, that would point to a particular function. Because if you think about it in terms of code, there are like 6 functions that exist in this code, right? There's polygons, 2 functions, there's triangles, 2 functions, and then there's rectangles, 2 functions. So for each of these classes, there's a little vtable stored somewhere that says, hey, for the rectangle, I'm rectangle's vtable, and I'm telling you that I need you to point to this function and to this function, or this function and this function. Now, the tricky part is that the vtable, this is all about memory really, a vtable is actually an extra field, an extra member, if you will, member property, whatever, of each object that's created. Pretty sure. I don't think it's related to the class. Just triple check. So how you can then imagine it is like you have your like class up here. It always goes south. Then you have like object 1 here, object 2 here, and object 3 here. Now they're obviously going to have like 2 ints themselves, right? They've got 2 little properties. And the reason we talk about C++ being a lightweight abstraction is because if we're not virtualizing things, if we're not using all this virtual override stuff, we don't need to add any extra weight to these objects. But once we mark something as virtual, what we are then going to have to do is we're then going to have to store another field on each of these, and maybe make it blue here, and each of those are a pointer, and they are a pointer to a vtable somewhere, right? So imagine them as like, basically once you start doing virtual stuff, your object gets a little bit bigger because it has to actually have a reference to something so that when the program is running, it can figure out who do I look up to figure out who I have to talk to figure this out. So vtable stored, these are the vtables up here, right? It's not that the vtable is stored in your object. That's not my point. My point is the vtables are written somewhere, but you actually have to reference them in your object. That's where that structure comes from. Yep, so this might make more sense now. A vtable is an array of function pointers. They say which definition each virtual function points to for that class. If the vtable for a class is not empty, then every member of that class has an additional data member that is a pointer. Every member of that class has an additional data member that is a pointer to the vtable. So that's what we're saying is like, so what they're saying here is that a vtable for a class is empty if there's no virtual stuff. It doesn't exist, basically, right? Once you start adding or putting virtual on functions, and you're going to have to go into subclasses and stuff, the vtable now exists because we had to define stuff in it. And once the vtable exists, all of the objects of that class type now have to have a pointer to that vtable. So again, main reason I'm stressing this is because this, the whole lightweight abstraction thing, this adds cost. Because imagine you have a small class now that might have 10,000 instantiations of it as objects. They're all now going to have 8 bytes to them, which is now going to be 80,000 bytes, or 80 kilobytes, which isn't a lot. But again, typically people who are writing these languages are trying to get higher performance code a lot of the time, which that takes up more memory. More memory will take up more clock cycles, having to do stuff, etc. When a virtual function is called on a reference or pointer type, then this is what the program does. It follows the vtable pointer to the vtable. It looks for the function, and then it follows the function pointer at the vtable to call the function. All right, so if we imagine this piece of code here, where we have polygon, right? Okay, I'm trying to think of a way, because you're all staring at me like you don't know what I'm talking about, which is my fault, not yours. Here's the point. Let's go back to a previous piece of code. If we have a look at this piece of code for a second, right? Now, the original version of this, when we called print class name, it wasn't a reference. Object slicing problem, it's always going to print out the base class's type. We've established that. I think you're all absorbing that information. Once we add a reference, it was still printing out. Let me get rid of the virtual, sorry. Forget the virtual part for a sec. Once we added that reference, it was still printing out the base class type, even though the object wasn't getting sliced. So it was a reference to the whole subclass object, all 4 parts, but we still printed out the wrong thing because all it had to go on was the base. And this, again, makes sense because I'm like, hey, I am base type, print out get class name. OK, base type, there's the function. Once you add virtual, what ends up happening, this is what you should imagine, right? Once I've done this, now, and I might get the tiniest detail here wrong, what happens is there's some magical thing happens, like where all of these classes now have this property that you'll never see, right? It's hidden deep in the program, if you will, called a vtable. And once that vtable exists, what goes on is that when I say base.getClassName, when I try to call a function on an inherited type that has a vtable, it says, well, I know that you're some kind of inherited type where you might have some virtual function thing going on. So what I'm going to do for you is instead of just say, because you're a base, I'm going to go call the base function, I'm actually going to go look up your vtable, right? Because it's got this little pointer inside of it. Because it's still a subclass, right? Even though it's like a base class reference, the actual object is a subclass. So it goes to the subclass's vtable, and this vtable here will be a list of 2 function pointers. And what it's going to do then is it's going to say, well, 1 function pointer in this case. It's going to say, well, hey, the get class name for me is this one. It's not this one up here. It's this one. And again, that's basically how this works here. So if we trace this back now, the vtable, these things in the middle here, these are think of them as 8-byte function pointers. So take you through it one more time, and I'm repeating myself a lot. I'm just throwing at it different ways. This over here is the data stored within an object. So imagine for these polygon examples, each object that you create of a class type is going to have an 8-byte height, an 8-byte width, and an 8-byte pointer. That vtable pointer points to this, which is an array of function pointers. So if you have a subclass like triangle, the vtable has an 8-byte pointer and another 8-byte pointer that says, hey, if someone calls sides on me as a triangle, please go use the triangle. That word triangle there is really important. Please go use the triangle version of sides. But if someone calls area, use the triangle version of area. Because if we go back to our kind of semi-butchered code example, if we have a main function here like this, think about it. If I go and create a triangle for a second, triangle, sure, call it triangle T. If I go and create a triangle and then I say, yeah, well, t.sides. I just want to print out t.sides. This is easy. It's of type T. You don't need the vtables for that. However, again, let's imagine for a second, I actually said, you know what, I'm going to have a polygon type called P, and it's going to reference T. What happens then if I call P dot sides? Same example we've seen before. But what we're saying is, because there's a virtual here, the vtables get created, and when I call P dot sides, it actually says, hey, I know that my kind of like invoked type is a polygon, right? I'm a polygon reference to a triangle. I could be a polygon reference to a rectangle, a polygon reference to a triangle. But what I'm going to do as a polygon reference to a triangle is go look in the triangle object. I see it has a vtable. That will tell me which function to call. It tells me I should call triangle sides, and then I'll call triangle sides. So the reason I like these vtable things is because I actually think this concept is hard to grasp if you just try and think about it like a programmer, because it's just confusing, right? Like, it's just a very confusing idea. But if you think about it, like, what would the approach be if you were designing C++ in a way that overriding functions should take up the minimal space possible? It actually makes a lot of sense, because we're just saying that, hey, every class has got this little thing. Now, let me see if I can let me see what we can do if, this is probably going to be a massive piece of code and not really of much use to us. But I'll see anyway what happens if I dump it in here. It's probably going to be gigantic. Woo. Yeah, so look, I'm not an assembly x86 interpreter here, but somewhere here, these vtables should exist. And they probably do exist in plain sight, and I'm probably just not very smart. Hey, we found them. They're right there. There you go. That's just in the binary somewhere. So what they're saying is we've got a vtable for the subclass, and we've got a vtable for the base class. These are the vtables. So I know I'm talking to myself. This middle column here, all of this stuff, these arrays of function pointers, they are stored in data. They do not add like RAM to your program, right? We're not saying that the vtables take up more space for your program to run. What we're saying is that each object you create will now have an extra like pointer in it that will point to this stuff here. It's a little bit like, if you're not sure what I mean, another example is you write a C++ program, we've seen these before, where I say char star s equals Hayden, and then I standard C out S0, right? Really simple program. Now, how much memory does this program occupy? Let me actually just open this up again. Yeah. I hope it doesn't get really big now. It's not too bad. Yeah, so in this case, again, like, and I don't want to forget rid of that. Yeah. Yeah, so a good example. Hayden here, because it's a string literal, it's stored in the data part of the code up here, and when the program runs, it doesn't actually go and malloc anything or put anything on the stack as far as I understand it. Maybe it does. But the point is, it's in data, it's just referencing that. Like we created a pointer here. This pointer takes up space, right? It's an 8-byte pointer, but it's just pointing to a piece of the compiled binary. And it's the same thing here with vtables. So these are the vtables, which is this stuff in the middle. It just makes the binary bigger. It doesn't use more memory. However, the vtable pointer that we have to add to every object that's created is an 8-byte penalty multiplied by the number of objects that exist at a time. And all those particular 8-byte pointers do is point to that data element. They literally point to this part of the binary. This is just code in the binary like string literals that they point to. You might think, why do we need to point? Why does every single object need to point to them? This is kind of where we get into the dynamic polymorphism part, because the very nature of this is that we don't actually know which version of something is going to be used sometimes until we call it, which is kind of where we get into, like the original example here was like you could pass in many different types to this function. And when Vtables exist, it'll look to that Vtable to figure out which one to call exactly. Now, there's actually a few things to go, but they're a little bit quicker to run through. Let's take a very targeted 5-minute break. Oh, sorry, one more question first. Yeah.
If a class has a vtable, will compilers still check the vtable even if the particular function can't be overridden?
If your question was sound, my brain is slow. So,
So the class has a vtable.
yes.
The particular function can't be overridden. Will the compiler still check the vtable to make sure?
I'm not 100% sure, but I think so. I think once something becomes virtual, it's all kind of like up in the air now, and a vtable exists and they have to check it. But it's hard to say because maybe that's not true too. Because some of this stuff also comes down to compilers. Sometimes there's things that we teach and then it turns out compilers just like make it more efficient. But I'd assume that it does for now at least. Good question. All right, let's take a 5-minute break. I want to get back and do it pretty quick because we have lots to talk about. So, yeah. Okay, so there's like, glancing over some of these slides again, there's a lot of stuff around compile. So again, the origins of this course were very compiler heavy. We've slowly been stripping some stuff out and focusing more on the programming. So there's a bunch of stuff on this slide to do with like, if a compiler does this, then it's going to look that up in the Vtable. I think we've done that kind of stuff to death. Typically, when someone learns C++, they probably aren't going to be going deep into Vtables, because again, that's a compiler runtime specific thing. However, what this slide touches on, which is important, is that the addition of final as a keyword is used to basically say, this cannot be, this is no longer virtual for any subclass. Because you imagine a case where you have, like, say, class A, B, C, D, and they all inherit each other, right? A is the super type, then B is a subclass of that, C is a subclass of B, D is a subclass of C. Once you mark A as virtual, you're kind of implicitly saying that like this may be overridden by anything in the chain further down. And final is a keyword that you can throw in after the override to basically say, no, this is it, that's the last time it's going to get overridden. So let's say you have class A that creates a virtual function and class B that overrides it and marks it as final. Nothing else under that can now override it. This is getting into a little bit of detail.
Can you have virtual and override at the same time?
I can't see why you would or need it. Maybe, but I haven't seen that.
But then how can C override B?
Oh,
B does that.
yeah, sorry, I understand what you mean. Yeah, probably. I mean, the funny thing with this stuff too, because we always get questions from students, that are kind of like, should this be virtual, should this be override? And the good thing about a lot of this stuff is because the compiler is quite finicky, you can just try it out a lot of the time. So just like kind of add stuff. And if something isn't there, you'll notice immediately because your code isn't working. I'm going to leave that or come back to that because that's getting into a bit of depth with final. And I want to keep moving on because we got 30 minutes left. So this is an important topic, abstract base classes. Who remembers this from another OO course? Did any of you do an OO course at some point? Maybe they don't teach it. I don't know. Things are different. Abstract base classes. So in a nutshell, abstract base classes are base classes like Polygon that you can't construct. So they're classes that have a definition. Well, I shouldn't say you can't construct it because technically they're constructed by the subclasses. But I think of it like that. So if I have a polygon, like you think about this example we had before here, polygon's sides are 0 and polygon's area is 0, right? That's a silly object. So I don't want someone making one. So if I mark polygon as an abstract base class, you can't make a polygon. You can use the polygon class to create a subclass and make that subclass that contains polygon stuff, but you can't just make a polygon. I don't have a good example for you. Thought about icing on a cake. No one just makes icing, right? You don't just make a polygon. Now, different languages will kind of define these things differently, but that's what all of that kind of says here. If a class has at least one abstract pure virtual in C++ method, the class is abstract, it cannot be constructed. So basically, what that's saying here so I think abstract and virtual, okay, this is what we're looking for. There's a lot of words being thrown around here, and I'm just trying to quickly resolve them. So a pure virtual function is one where you mark it as 0. That's kind of, I probably did gloss over this one a little bit too quickly. So if you want to mark a function as abstract, basically like a polygon doesn't have an area and it doesn't have sides. So I'm going to mark my area and my sides function for my polygon as I don't want you using this because it makes no sense until someone inherits it and overrides it. That's when we can mark it as a pure virtual function, right? So this here is marked as a pure virtual function because I mark it as virtual and then I say it equals 0. Funny syntax, right? It'd be nice if they just wrote in something there like abstract or like whatever, but we mark it as equaling 0. And this is like an important point here. If a class has at least one abstract method, the class is abstract and cannot be constructed. It can, however, have constructors and destructors. These provide semantics for constructing. So this is what I meant before, how I was like, you can't construct an abstract base class. But what we're really saying here is that you cannot abstract the class. However, it has constructors and destructors, so its subtype can do the construction and destruction of it. But the point is, once a function starts to have pure virtual stuff in it, I don't believe you should be able to actually create it. But this is OK because typically what I see a lot of is that you'll either have a class that is abstract or not. And if it's not abstract, nothing will really be a pure virtual. And if it is abstract, everything in there will be a pure virtual. So they've got some contrast here, which is like we have a shape class. And this is what we've seen in previous examples, where we go and define a function called draw. And we just say that someone can override it. So I can use shapes draw in the first case. Someone can just override it. The person who's deriving your class or writing that subclass may forget or choose not to override it if they want to. If you were to just write something like this, this would fail at runtime because the compiler would simply look for a definition if you don't define it anywhere, right? Because this one's a definition, whereas this one's just the declaration. But what we're saying is, in the case where you actually mark it as a pure virtual or mark it as abstract, you don't need to define it because you're literally saying there is no definition for it. Someone has to override this. I am now a class that has some stuff someone has to override, so you can't go and create versions of me. Hope that makes sense. Okay, you're getting tired. Okay, creating polymorphic objects in a language like Java, everything's a pointer. This allows for code like this on the left. That is some small code. So let's have a look at it together. What we're saying is that in Java, you can go and do something like this, right? Or, that's C++ in Java format. If you're writing it as Java, it might be, what's Java? It'd be like an array list of Polygon or something. I don't remember how to write Java. Array list. Then you say like array list.push or whatever the hell it is. And then you might go and create like a new triangle. And you'll go, was it new triangle? Whatever. You go create a new triangle and a new rectangle. And then for fun, you'll go and create another new triangle and another new rectangle. This is Java S. This kind of works. And the reason this works is because Java's using references for everything. You're just not really looking at it. You can't do that in C++ because in C++, we said at the very start, we have value semantics. That word we threw out, which is a strange, scary word, it just means that everything in C++ is about values, not about references. So these are all values. This is an actual base class, an actual subclass, an actual subclass. We can't do that. One of the problems then becomes, well, how are we going to have an array of different types, right? Like if we want to have an array of like many different base classes and subclasses that are all still of that type base class, what are we going to do with that? And it's hard because like one solution is to be like, actually, we're going to go make a pointer, okay? Like Java does, right? Just less abstracted behind Java's, nice abstraction. And then we just go and start making random heap shit like this. Okay, that works. Now we're doing what Java does. We're just doing it in an opaque way in our control. But now you've got to go free all that stuff, which isn't good because that means you've got to iterate through this thing at some point and free everything. So what we are going to do instead is, as you might expect, the code here is somewhat clear, is that you might go and create I'm just going to copy it. It's quicker. You do this thing, but with the knowledge of our 5.3 lecture, which is this. So if you did actually need to create a polymorphic situation with, like a base type, like a polygon with many triangles and rectangles or whatever inside of it, you would go and say, actually, I do have a vector of pointers. They just happen to be unique pointers, smart pointers. And then when I go and add stuff in there, instead of doing new, I will go do make unique, right? So we just leverage that stuff we've previously learned. It's not too bad. But this is actually where, like, because when we talk about smart pointers, we often talk about it in this kind of like, oh, unique pointers and ownership and like concurrency and stuff. That was very academic, but in reality, it's just a great, particularly unique pointer, which I said is really common. It's just a great, easy way to get around the fact that you want to use pointers without all the scariness of it. So that's how we could create polymorphic objects and lists and stuff. Okay, lots to go through. Inheritance and constructors. Every subclass constructor must call a base class constructor. Yes. If none is manually called, the default constructor you use a subclass cannot initialize fields defined in the base class, right? So this is all fairly standard OO stuff. It's not really specific to C++, so I won't spend a ton of time on it. But if we do look at this case here, we have a base class that initializes the member inside of it, just the int. We give it an int when we invoke it. And then we have a subclass here where we have two examples. The bottom one's not going to compile. Let me just comment it out for a second. Where when I create a subclass, I take in a member and I take in a unique pointer. This one's like a R value reference to C++'s a head mess sometimes, isn't it? But this is how you do it, is if you have a subclass and you want to construct the parent class, you do it like this. It's like the initializer list. The first thing you do is you call the parent class and you give it its thing. Right? Same as in Java. In Java, it's a little different, though. In Java, like if you have a subclass, like in Java, it's like subclass like this. And then I haven't written Java in like literally 9 years. So you'll have like this here, subclass parent, and it takes in a member and like a linked list, whatever, right? But here you then call super member, right? If anyone remembers Java. You call super, that calls the parent class, that constructs the parent class for you. You always have to call that first in your function, and then you do everything to do with your subclass after that point. It's the exact same principle as Java in C++. It's just the way we write it's different. We do the construction there. That's like the equivalent of calling super in that case. So that's how we do that particular piece of construction. Abstract classes must also have constructors. Basically, if anything's being inherited, it needs to have a constructor generally, or it can default. The examples you saw earlier that we wrote, they all had a lot of default constructors in it because, if I just go back, here, you notice we didn't really define any constructors, which is fine because default constructors get synthesized, right? And if you have a default constructor, all it will do is go and default construct the members, the member properties fields. And if you have a subtype that inherits something and it creates a default constructor, all it's going to do is call the default constructor the parent type and then synthesize its own and do the exact same thing, right? So you don't need to define those things. It's more just like when you do define them, you need to make sure that you do actually invoke the parent class as well. Okay, so destroying some polymorphic objects. I kind of think we talked about this a little bit here, so we don't need to go too deep. I don't know why this would be a problem, though, because it would just create a base class and then a subclass which contains a base class and then destruct it. Yeah, I mean, okay, so sure. Here they're just pointing out that C++ would like you to always have a virtual destructor. for your base classes. We've kind of seen that before. Again, I don't want to spend 5 minutes talking about that. However, it's important to note, and this is why we teach lots of little tidbits about the course, when you do define your own destructor, the move constructor and assignments maybe can't remember about the copies, but I think it's the copies too. Because remember, back in week 5, we talked about the rule of 5, which was copy construction, copy assignment, move construction, move assignment, destruction. And we said once you define one of them, you have to define all of them, because once you define one of those 5, it's a signal to the compiler that it's not going to go and synthesize any. So this is a relevant thing because C++ wants you to make, if you have a class that's going to have subtypes, basically if you have a class you've made that is inherited and you have virtual stuff in there, just like you saw me have that compiler error earlier, then you do need to make your destructor default or define it, but you do need to generally mark it as virtual there. However, that does mean you have to go and do this stuff manually, which is actually largely what we got caught up with, if you remember about like 30, 40 minutes ago when I was trying to like push that random example through. I was having to define the copy constructor again and define the default constructor because C++ was just having none of it. It was like, you're making your own destructor, I'm out of here, you just have to tell me what to do at this point. So it'll warn you. Yeah, I'm pretty sure it warns you. Yeah, it should warn you. I think that one's pretty well handled by the compiler. Okay, I probably think this slide should be earlier in the lecture slides after the time we've spent on it today. 2 important terms, static type and dynamic type. Static type, dynamic type's easy. It's the type of the object. So when you make an object that's a subclass, it's forever a subclass. It's just that's its dynamic type. Yeah, but a static type is the type it's declared as. This is really this is really important for references. Now, why this is important is it's terminology that helps us understand how to talk about some things here. I create a base class, right? Its static type is base class. Its dynamic type is base class. I create a subclass. Its static type is subclass. Its dynamic type is subclass. I create a copy of subclass. Its static type is subclass. Its dynamic type is subclass. Sure, right? However, then we get down to these kind of more strange areas where now I'm creating this variable called base to base, right? It's a reference to a base class. A fairly wordy line. I'm sure you could rewrite it pretty comfortably as, I think this would work fine. I'm pretty sure these two things are the same, unless I'm tripping. So you're creating a reference to it, right? That's all it is. There's a base to base as a reference. Now in this case, and this is where things start to get interesting, the subtype is base and the dynamic type is base. But here's what's important. Sorry, the static type is base. The static type is this, right? Like base to base is a name, it's a variable. Its type is a reference to base class. Its type is its static type. Type? Yeah, static type. However, what that base class static type variable references is also a base class. So it's dynamic type's base class as well, right? So they're both base classes. But this is where things get trickier. This should be a static type of base class and a dynamic type of subclass. This is kind of the first example where they're splitting. And it actually makes a lot of sense. And the reason I mentioned this slide should probably be earlier is because it's probably an easier way to talk about this stuff. Because base to sub, or there's so many words being thrown around, let me just call this one frog. The frog variable here is a reference to a base class. That makes it a statically typed base class. What that's saying is like when the compiler, at compile time, it looks at frog and says, you are a base class type, because the compiler only knows that. But then when it comes to runtime, when this thing's actually running, when you invoke it, when you talk about frog, when you call a method on frog, if it has a vtable, during runtime, it looks up that vtable and says, what are you actually? OK, you're actually a subclass. I mean, it doesn't need the vtable to figure that out, actually. Don't get those two things conflated. But that's where we get those differences there. So in this one here too, this fails to compile altogether because you can't create a subclass reference to a base class. That makes sense. I can't create a triangle reference to a polygon. Polymorphism doesn't work that way. It works the other way around, right? I can have like I can have a parent type reference to a base type, not the other way around. So yeah, that's essentially where the terminology comes from. Static means compile time, dynamic means runtime. Static means the actual type of the variable name, and dynamic is what it actually is, if you look under the hood. Due to object slicing, an object that is neither reference or pointer always has the same static and dynamic type. What we're saying there is that if you have a subtype, right, really simple example, let's take the reference part out of this line here, right? Let's look at frog now. Frog, because it's no longer a reference, is experiencing the object slicing problem again, because we're copying it. We're copy constructing it in. So we take a subclass that's this big, and we try and shove it into a base class type that's this big, and during the copy construction, the bottom gets cut off and we just get left with this. And what they're saying there is that when we don't use references and pointers, but we just use copying, there is never a difference between the static type and the dynamic type, because in this particular case, after this is defined now, its static type is base and its dynamic type is also base, because we got rid of everything that was extra because we had to copy it into a finite amount of memory. So, so this stuff about dynamic and static typing sometimes being different is pertinent predominantly when it comes to references and pointers with types. More terminology. Yeah, this is really just saying like, non-virtual functions they can kind of figure out at compile time, whereas virtual functions they figure out at runtime. Again, we could go super deep on that stuff. Some extra terminology around types as well. I guess that's quite relevant. Upcasting is a term. It's when you cast from a derived class to a base class. We've been doing a lot of this in the lecture. We've been doing it with both references and pointers. If you create a dog, and let's pretend a dog inherits an animal, as we've kind of given the example, then when you do this and you say, actually, I'm going to create a variable called animal, which is just a reference. It's an animal reference to a dog, reference to an animal that happens to point to a dog. Because we would say, in both of these cases, animal has a static type of animal. It's a terrible variable name. The animal variable name has a static type of capital A animal and a dynamic type of dog. And in both of those cases, we have done what we've called upcasting, where we're essentially casting it to something up, that like inheritance tree. Downcasting, we don't really like to do this. I think the compiler will often kind of complain about it. Yeah, I mean, it does. You create a cat and a dog, and then you create references. Yeah, it's tricky. This is an interesting example. So I create a cat and a dog, and then I kind of upcast them to animal types. Now, this is really funny stuff, because let's think about this for a second. This should work intuitively to some extent, right? Because the dog and the cat, like think about this. Dog here, static dog, dynamic dog. It's just a dog. On this line, I turn it into an animal dog. Animal dog has a static type of animal, but a dynamic type of dog still. It's still a dog, right? It just happens that animal's pointing to it. And then I say, well, if it's still a dog, I would really like it if I could actually take my thing that says it's an animal that's actually a dog and turn it back into a reference to a dog. That's what I'm trying to do on line 9 here. But this doesn't compile, and I'm pretty sure the reason it doesn't compile is because all this compilation has to be done statically. So from the compiler's perspective, it's literally just being like it doesn't think that deeply about it. It's like, yeah, like look, an animal, which is what you are, your reference to an animal, you can't downcast that way, right? Even though it's actually its dynamic type is a dog. And this is why we kind of talk about static and dynamic typing, because the compiler is only ever concerned with the static type. It doesn't care what the dynamic type is. Static mean compilation. So if the static type of animal is this, it doesn't matter what its dynamic type under the hood is. It will not cast it because it's doing all this analysis statically. If you want it downcast, you have to start doing some funny things like this. Again, this is getting pretty heavy for the time we have, but let me just have a quick look. So I've got my dog, I've got my cat, I've got my animal dog, I've got my animal cat. And then if we want to downcast with references, what we have to do is basically do a static cast. So I have to take my dog and static cast it to a dog reference. Because remember, what a static cast is basically telling the compiler to, like, I don't care about your rules with types. I'm asking you to force this change, you know? And it'll generally, you know, do these kinds of reference changes and stuff. Though it is, yeah. Yeah, okay. Don't worry about the dynamic cast. We don't really touch on it in the course. The dynamic cast is a funny cast that doesn't try and preserve values. It tries to preserve bits. If you're not sure what I mean, go cast a floating point. Like, you know how you can cast a floating point of like 1.0 or like 36.0 to like the int 36, right? Go do a dynamic cast and you see what happens. It's a little bit different. This is kind of a relic before we stripped it out of the course, so let me just get rid of it. But what we're saying here is that you can use this funny static casting to do that. But like any static cast, it's not strictly wrong. You just need to make sure you know what you're doing, right? Like as a developer, you only write this if you're 100% sure it's actually going to work. Whereas this one's really tricky because you can do some funny things like this if you try, where you know, you upcasted a cat to an animal, so the compiler just thinks it's an animal, and then you try and statically cast the animal to a dog, but it's actually referencing the cat. And what this is saying here is that this is obviously a bad static cast, but in this case, the compiler will probably let you do it. It just then becomes undefined behavior, and then weird, wacky stuff happens. Remember, undefined behavior is that big, big, scary thing. Okay, a few more things. Oh, it's a lot of stuff. 3 slides. Covariance. You can go read more about covariance and contravariance. This deck kind of gets to the less important stuff as we get further back. What we're saying here is if a function overrides a base, which type can it return? Ooh, that's an interesting question. We have a base here, which is a function called getFavoriteAnimal, and it returns a reference to a land animal, and it's virtual. Then we have our derived class, where we try and override that a few different ways, where in this case it's like you say, I would now like it to return a reference to an animal instead. Now, this is all very heady stuff. All very heady stuff still. Remember, when we override things, we generally preserve the name and the return type and the parameters, you know? We're just changing the implementation of the function. So if we override this function, it should still be a function called getFavoriteAnimal that takes in nothing and returns a reference to a land animal. What we're trying to talk about here is that you can actually tweak that a little bit when you override it, if you'd like, because this is a normal override here, right? This middle line. We're just copying the function, and we're you know, different implementation. We can actually also override it this way here if the return type itself is a subtype of the original return type. Where basically all we're talking about here is like polymorphism when it comes to return types. Because dog, I mean, it's not written anywhere, but dog is clearly a subtype of a land animal, it will work. But an animal is a supertype of a land animal, so it won't work. So that's what we're talking about with covariance. With contravariance, these are big words, but basically like covariance is referring to return types in polymorphism, and contravariance, I hate these words, is like referring to the parameters. Because if we look at this particular slide, we're asking ourselves, if a function overrides a base, which types can it take in? So covariance was about what can we do with returns, and contravariance is about what can we do with things that are passed in. So you take that example, flip it around, we now have a function called useAnimal that returns nothing, but it takes in a reference to a land animal. Well, what did we just learn from the previous slides? We learned that, well, we can override it totally normally just by overriding it with the same parameter, land animal. But what's funny about this is the rules flip themselves the other way around, because you can't actually pass in a dog, but you can pass in an animal. Makes sense when you think about it intuitively, right? Because using and returning something is kind of on different ends of the spectrum. Because if I normally can use a land animal, I should only be able to use that or less. And an animal is going to be less of a land animal. Similarly, when I return something, if I'm normally returning a land animal, I can only return that or more. I can't really return like that or less. So these concepts of covariance and contravariance are just wordy ways of saying something fairly intuitive, which is that you can change the return types and parameters when it comes to references, just references. When it's polymorphic references, you can't change it to an int or something. You know, it has to be like a type or a subtype. So all these type, subtype rules apply to parameters and return types when they're being overloaded. Default arguments and virtuals. We got 2 streams left. Default arguments are determined at compile time for efficiency's sake. Hence, default arguments need to use the static type of a function. Avoid default arguments when overriding virtual functions. All right, we got one funny little piece of code here called default. Let's quickly have a look at it. It has a function called printNum. Default argument of 1. You pass in I as 1. And then we have a base here where we have a default argument of 2. Cool. I go and create a derived class, a subclass, and then I go and create a pointer to my derived class. We could do this with references if we wanted to. I think we're just having a bit of fun. And then we see what happens here. What would we expect to happen when I call derived.printNum? Now, if you're using the principles of Vtable and stuff that we're familiar with, what you would expect to happen is that it should print out, print out 2, and then base should print out 1. Just let me run that. Make default. 7.1 default. Yep. So we get that. Now, this works for, like, where this is strange for us is that it should, in theory, based on our intuitive understanding previously, print out 2 in both cases. Because the dynamic type of this is the same. We only created one. This is what we created here. This is the thing. It's a derived class. This is just a pointer to a derived class, right? So both of these variables, derived and base, have the same dynamic type because it's the same actual object. But they have a different static type because one of them is referring to it polymorphically. What this slide is saying to you essentially is that when it comes to default arguments, we have to be careful because the people who defined how C++ works decided to, for quote-unquote efficiency's sake, say that the default arguments are based on the static type, not the dynamic type. Right? Most other things with this today have been like all the dynamic type, like the Vtables and the functions, but it's just like you can imagine it from the perspective of like there's just like more information to figure out, and it's not that big a use case. So just be very careful when it comes to C++ and default arguments and all of that. All right, so last thing. This is actually kind of fun. So we're going to have a fun last 5 minutes. Be really quick. Construction of derived classes. You've probably inferred a little bit of this already as we go forward. Base classes are always constructed before derived classes. So if I've got like animal, land animal, dog, and I create a dog, it goes and creates an animal, then it creates a land animal around it, then it creates a dog around it still. So if I have an animal, a land animal, and a dog here, and then I go and create a dog, what actually happens in this case is that dog calls land animal's constructor, land animal calls animal's constructor, right? They kind of super each other up the chain. Animal's members get constructed using the initializer list. That's normal class stuff. Animal constructed body runs, normal class stuff. And then the same thing happens on the way down. So you imagine when I create a dog, it kind of like shoots its way up to the top of the tree and then constructs itself back down until the object's created. Now, fun little piece of code here is if I have an animal and a land animal, does this code run? These code, tell me I have one that runs today. We don't have one that runs. This might be a bit. Yeah, this particular example, Yeah, you can go read that if you'd like and spend a few minutes looking at it. It's just talking about the case where, like, when you create a dog, yeah, it's a bit funny. So this one, if I go and create a dog, same example, animal, land animal, dog, what it's saying is that my constructor for land animal calls run, right? Run is virtual and it's overridden in dog. However, if a member function is called during construction, it doesn't do anything with dynamic binding. It's too complicated, to figure that out. So it's literally like, if I'm in the middle of constructing land animals, so anything in the constructor doesn't apply any of those rules that you understand, because construction's a funny little process. So in this case, it calls this run here, whereas if I call dog.run after the fact, it will call this run here. So during construction, nothing really happens there. When it comes to destruction of derived classes, it's the exact opposite of construction, and we have already seen this before, which is that we call dogs destructor, we destruct all the members of dogs. We call land animals destructor, we destruct them. We call animals destructor, and we destruct them. So we just move through in that pattern as well. And then last thing, if a class is partially destructed, we cannot perform dynamic binding either. So same thing we've seen before, where if I have a destructor calling a function, which is a level of complexity I'm sure your code will go nothing near, having many derived classes and virtuals, and then you have a destructor that's deciding to call a virtual member for some reason, we're simply saying that it will do exactly what the construction does. Destruction, like construction, is a funny little thing. So it will simply go, I'm just going to call my static type. I'm a land animal destructor. I'm going to call the land animal run. I don't care about Vtables. I don't care about any of that. And that's it. Cool. Well, we haven't had any questions today. And it's 8:58. So hopefully that was interesting. Thank you.